welcome all of you for the next lecture on photoelectric effect, which is a part of what we may broadly call as set of lectures on modern physics. Because after discussing photoelectric effect, we will be discussing the Bohr model of the atom and then the matter waves as postulated by de Broglie, and after that we will be going on to discuss nuclear physics. So far what we have done is to spend a great deal of time studying what the experimental results on the so-called photoelectric effect tell us. In fact, all of last lecture was a detailed discussion on the findings made by Hertz, Lenard and Millikan in their very careful and very famous experiments, and we were able to extract the universal features of these experiments. So what we are going to try to do today is to point out that these experiments actually show that there is a deep problem, in fact a big lacuna in our understanding of electromagnetic theory. Electromagnetic theory and especially properties of light seem to be very well established in the earlier experiments, from the earlier experiments through so-called the wave properties of light. But here we are going to encounter that we will face serious problems if we just adhere to the wave property of light. That is what we want to show. And we also want to show how a very radical proposal from Einstein actually solves this problem. It does not solve the problem of classical electrodynamics or classical theory of radiation. It does explain what photoelectric effect is in a new language, but eventually the development of quantum mechanics reconciled both of them, but that is beyond the scope of your study. One thing that we have to remember is that the paper on photoelectric effect was written by Einstein in 1905. So let me spend some time on the timeline. We know Hertz started his experiment sometime in late 1880s, 1890s, and the experiments of Lenard went on till 1903. So we have 1903 experiments. Lenard. And the great Millikan kept on performing experiments from 1904 to 1915 over a period of 10 years. His most famous experiment, the most celebrated experiment, actually came around 1915. But Einstein wrote his famous paper in 1905. So this was a theoretical explanation. So you people may know that in 1905, Einstein was a young man of 26 years old. He did not hold any position in any university. He was actually a clerk in the Swiss patent office, and he wrote this paper. Even more important is that he not only wrote this paper, he wrote two more fundamental papers. So 1905 is called Annus Mirabilis. This is Latin. So if we translate it into English, this will call the miraculous year. So Einstein wrote three fundamental papers in 1905. The first paper that he published was on photoelectric effect. And then he published his paper on special relativity. And the third one on Brownian motion. All these three papers are of fundamental importance to physics. They changed the way we look at physics and the way physics allows us to look at nature, to describe nature. And most of you have, of course, heard of special relativity. You will certainly learn photoelectric effect. You have been learning about photoelectric effect in this course. The paper on Brownian motion is also extraordinarily important because this is the paper which actually showed how to verify the so-called molecular hypothesis of Boltzmann. So this is a theoretical paper on molecular hypothesis. So in your kinetic theory of gas classes, you would have heard of equipartition of energy. The gas is made of a large number of molecules. They will collide with each other, so on and so forth. One needs a direct experimental evidence for that, for which it was not there. The Avogadro number, etc., they were all hypotheses. It is this fundamental paper of 1905 on Brownian motion that actually allowed experimentalists to directly measure the Avogadro number. These experiments were in fact performed by the French physicist Perron, and he also got a Nobel Prize for that. And Einstein himself got a Nobel Prize for his fundamental work on the photoelectric effect. So there is much debate on why he did not get a Nobel Prize for special theory of relativity. There are many, many reasons, but for us, the important physics reason is that Einstein himself said that special theory of relativity was a cakewalk compared to developing the theory of photoelectric effect. Because for special theory of relativity, he had the earlier works of Maxwell. Maxwell's equations were there. Lorentz transformations were already derived by Lorentz. All that he had to do was to put them together in a coherent way. I mean, that is what he said. We don't belittle his work. But photoelectric effect, and it was a completely difficult experiment to understand, and it required a radical explanation which required much more courage than what was required in the case of special theory of relativity. So it is no wonder that he got a Nobel Prize for the photoelectric effect. So what I am going to do today is to briefly summarize what the experimental results are. It is good to summarize before we start with the theoretical discussion. Then I am going to show what the great conflict between the experimental result and the classical theory is. It is not a small discrepancy, it is a very, very large discrepancy. I am going to show you that. And then I am going to tell you how the concept of a photon arose and how Einstein was able to use it very profitably. This is a model that he proposed, but it is a very, very powerful model because at the end we are going to show that this model can explain one more phenomenon which seems to be quite unconnected, and that is what is called as the Stokes law. And there we are going to conclude a discussion on photoelectric effect. So let us start with a brief discussion of facts and then look at the prospects. Okay. Let us get into a recap of what the photoelectric effect is. This is a graph that I have shown you earlier, and this is essentially a reformulation of the famous experiment performed by Millikan in 1913. On the y-axis, what you have is the maximum kinetic energy of the photoelectron. So what is happening? So let us remember that, recall that. So you have a metal surface and you have radiation falling on it and it is emitting electrons. That is what we have. And these are collected. These are not exactly collected. So what you do is to put a plate here and apply an opposite voltage, that is a force in this particular direction, and you ask what is the voltage that I have to apply to stop all the electrons that are reaching the plate. That means I should be able to stop even the fastest moving or the most energetic electron. So that voltage multiplied by the electron charge will give the maximum energy. Maximum energy. What you do is you keep on changing the frequency of the radiation. So let us come back to this figure. We keep on changing the energy of this radiation and ask, how does the maximum kinetic energy of the electron change along the y-axis? And the maximum kinetic energy is simply nothing but the stopping potential. The stopping potential is the minimum potential that is required to stop all the electrons. So when you plot them, this graph clearly shows that you are going to get a straight line, and the slope delta E by delta nu, it has the dimension of energy into time or angular momentum. That is a universal constant. This experimental result is for sodium, and the x-axis is in electron volts. So that is what you have, and the y-axis is also in the electron volt. The same experiment can be repeated on zinc, on nickel, on many atoms, on gold. The frequencies will be different, the maximum photoelectron energy will be different, but the slope is a universal constant. That is the most important thing. Slope is a universal constant. So we have two tasks cut out for ourselves. How do I understand this linear behavior from whatever I know from electromagnetic theory, and what is the meaning of this universal constant? So these are the two jobs that are cut out for us, and let us see what we can do with that. So whatever I told you in words, I have collected again in this particular slide. These are the important points. And basically what we are going to look at is universality coupled with the interplay between the intensity of the radiation and the frequency of the radiation. So here is point number one. First of all, we notice you take any metal, there is a minimum frequency that is required for photoemission. If the frequency is less than that minimum frequency, the threshold frequency, you can keep on increasing the intensity, but no photoelectron will be emitted. That is an experimental observation. Now once I cross that minimum frequency, you cross the threshold, then as I keep on increasing the intensity, more and more electrons are emitted. That is the next thing. So what is the statement that we are making? There is a threshold frequency. Below the threshold frequency, no emission whatever the intensity may be. And after the threshold frequency, so let us call the threshold frequency nu naught. If nu is greater than nu naught, then it is proportional to the intensity. So no emission below minimum frequency. And how does it depend on the frequency? As I keep on increasing the frequency, there is a linear relation between frequency and the stopping power. This does not depend on intensity. The stopping power does not depend on the intensity. The total number of electrons which are emitted depends on the intensity, but the stopping potential does not depend on the intensity. It depends only on the frequency. That is what we find in this particular figure. So the stopping potential is exactly the same as the maximum kinetic energy, and this is something that we have to understand. And these results are actually mysterious. They appear to be very simple because most of the time when we plot graphs in our laboratory, we want to have a straight line. Even when it is not a straight line, we convert our units such that we are going to get a straight line. But here we have a serious problem. Because if my electrons are getting ejected from the metal, that means my electrons are bound to the metal. If they are getting ejected, you have to supply energy. And where does the energy come from? The energy comes from the radiation. Radiation carries energy, radiation carries momentum. That is what Maxwell taught us, and that is what was verified by experiments. All of us know how to do an experiment. Take a lens, focus sunlight on a sheet of paper, and the sheet starts burning. We have all done that when we are children. So radiation does carry energy. So that is not a problem. The real problem is in the expression for the energy density. I have already discussed it earlier. I am reconciling that. The expression for the energy density is given by epsilon naught E squared, where E is the electric field. Now, if there is a monochromatic plane wave, remember that. So, let us go through that quickly so that we are not going to miss the point. If you have a monochromatic plane wave, that means my frequency or wavelength is fixed. Then my electric field is E naught, let us say sin kz minus omega t. K is the wave number and omega is the circular frequency. Then my energy is nothing but epsilon naught E squared. That is what I have, which is epsilon naught E naught squared sin squared kz minus omega t. So, at any given point, the energy oscillates between 0 to epsilon naught E squared. In the visible range, the frequency is of the order of about 10 to the power of 14 hertz or 15 hertz. That means, in 10 to the power of 14 or 15 seconds, it is oscillating, in 1 second it is oscillating 10 to the power of 14 or 15 times. We cannot measure that. So, what you do is to look at the average, and that is going to give me epsilon naught E naught squared by 2. That means, all reference to the frequency or the wavelength goes away, your energy density depends only on the amplitude squared, E naught squared, which is the magnitude of the electric field, the maximum value that the electric field can take. That means, if energy is being transferred from the radiation to the electron, that transfer should depend entirely on my E squared. That is what this sliding is showing to me. U equal to epsilon naught E squared implies U equal to epsilon naught by 2 E naught squared. It should not depend on the frequency. However, if I go back and look at this diagram, this great experimental diagram, my x-axis is actually the frequency, and you see less than 4.5 electron volts in this particular diagram, there is no emission. You can keep on increasing the intensity, there is no emission. Therefore, we are in for trouble. We are not able to understand this very elegant, this very simple, beautiful figure from the classical theory of electrodynamics. So, what do we do now? Now, there is one way of qualitatively seeing the discrepancy between the classical theory and the quantum with this photoelectric effect. There is another way of estimating the discrepancy between what Maxwell tells us and what the experiment is finding. Now, let us imagine that an electron is bound to a metal. So, there is this metal and there is this radiation that is falling, and there is an electron which is sitting here. A good question to ask is, how does this electron get liberated by this radiation? So, what is happening? So, if you imagine this electron is bound to the lattice through a spring, is that right? So, that is how we imagine the atom to be. Then this radiation comes, it hits the electron, therefore, it will start oscillating. So, what you are getting is a forced oscillation. Which you have studied in your mechanics, which you also will study in your LCR circuit, so on and so forth. You have a forced oscillation. So, if my electron has a natural frequency omega naught, and if the radiation is coming with a certain frequency omega, what happens? As you keep on hitting, the electron will start oscillating with more and more energy, and eventually when the amplitude keeps on increasing, and eventually when the amplitude hits the breaking amplitude, at that point the spring snaps, then you say that the electron is liberated. So, what I can do is to ask, what is the time required for an electron to get liberated if I keep sending my energy? That is the question that we are asking. And that is a very, very easy thing to estimate. So, what we are going to do is to ask how much energy is absorbed per unit time by the electron. So, let us come back to this slide. So, the energy absorbed is energy per unit time which is falling on the metal divided by the total number of electrons. That is what I want. So what I have a plate here, the radiation is coming like this. So I am asking how much of radiation is falling per unit time, per unit area, and I am assuming that all of them are going to be absorbed. Then I know how much is absorbed by each electron because I know the number of electrons in that area, and then I will find the time required, and that is what I have written here. So I take the energy density, I will multiply it by the area, I will multiply it by the speed of light, so that will give me energy falling per unit volume per unit time, and I will divide by the number of electrons, which is actually the density of the electrons. And what should that be? That should be nothing but your stopping potential divided by that E absolute. Your time required must be nothing but that, and we want to look at that. So here is some relevant data. So let me come up here and you will get the complete information. These numbers are real numbers, so please take them seriously. I am looking at sodium. Sodium has a work function of 2.36 electron volts. Number of electrons, by that I mean the electron density, is 10 to the power of 19. The wavelength is about 300 to 400 nanometers, let us say. Intensity is 10 to the power of minus 6 watt per meter squared, because I calculate that. Therefore, the energy per atom that you supply is 10 to the power of minus 25 watts per second. You are supplying 10 to the power of minus 25 watts per second. Now you can compute how much is the energy for the electron, how much is the time for the electron for it to gain an energy of how much? About 2 electron volt or 3 electron volt. Plug in all the numbers. If you did a computation, you will get 2.6 into 10 to the power of 6 seconds. So please take this as a home assignment. Note down all these numbers. Work function is 2.36 electron volt. Density is 10 to the power of 19. Wavelength is 300 to 400 nanometer. I am giving you the intensity, 10 to the power of minus 6 watts per meter squared. All these are the numbers employed in the experiment, and the time taken will be 2.6 into 10 to the power of 6 seconds. How much is 2.6 into 10 to the power of 6 seconds? Well, you have 24 hours in a day. Then you multiply it by 3600. That gives you the number of seconds in a day. And then you multiply it by 30. That gives you the number of days in a month. So if you multiply this, you are going to get 2.6 into 10 to the power of 6. That is what you are going to get. So that means that this number corresponds to waiting for 1 whole month. That is what we are saying. So take the Millikan experiment or the Lennard experiment. They have very, very low intensities, but sufficient frequency. This low intensity radiation is coming. The energy absorbed depends on the intensity. So that is the calculation that I am doing. If the classical theory is correct, I would have had to wait for 1 whole month, which is 2.6 into 10 to the power of 6 seconds. What is the real time required? The early experimentalists told us that it was instantaneous. It took place immediately. No, we don't know what the meaning of immediate is. That depends on the clock that you have. So let us imagine that Millikan had a clock with a resolution of half a second or even 1 second. That means there is a discrepancy of 10 to the power of 6, a factor of 10 to the power of 6. I will give you an idea of what 10 to the power of 6 is in a minute. The radius of the earth is about 6400 kilometers. The radius of the earth is about 6400 kilometers. So that is 6.4 into 10 cubed. So it is 10 to the power of 6 meters. So it is like confusing your meter scale to be the radius of the earth. It is as bad as that. But actually it is much worse than that, because today we know that the real time that is required, we have much, much better clocks. Okay, the real time required is 10 to the power of minus 9 seconds. All transitions take place over 10 to the power of minus 9 seconds. Therefore, if you look at this slide, what is it that we are finding? Classical theory says 1 month, which is 10 to the power of 6 seconds. My experiment is saying 10 to the power of minus 9 seconds. Therefore, the discrepancy, the ratio is 10 to the power of 15. It is a mind-boggling number. 10 to the power of 15 is enormous. It is like the lifetime of a person. So, if classical theory were correct, if Millikan or Lenard had spent their whole lifetime during their experiment, maybe they would have found a few electrons, and that would not be photoelectric effect at all. So, there is another estimate for you to see the discrepancy. The Earth-Sun distance is 10 to the power of 11 meters. So, that is the distance between the Earth and the Sun. And size of a dust particle is about 10 to the power of minus 5 meters, 10 to the power of minus 5 to 10 to the power of minus 6. So, what you are saying is that the dust particle is so big that it fills all the space between the Earth and the Sun. If I made such a statement, I would be stark raving mad. Nobody can make such a statement. So, exactly the same way, once you accept the validity of these experimental results, it is impossible to reconcile the classical theory with whatever we have observed. So, in other words, there is a modern terminology which people like to use. We need a very drastic method. You need what? A surgical incursion. You have to do a drastic surgery, right? That is what we have to do, and that is exactly what Einstein did when he gave his explanation for the photoelectric effect. You might wonder whether the 3 papers of Einstein had anything to do with each other at all. The paper on special theory of relativity, the paper on the Brownian motion. Actually, all the 3 of them have to do something with each other. Einstein is speaking the language of a photon gas, you will see, and of course he speaks the language of an atom because the electrons are coming. Therefore, you need validity for the molecular hypothesis, which the Brownian motion gives. The photon hypothesis is not only inconsistent, it cannot be understood from classical electromagnetism, it also cannot be understood from the viewpoint of Newtonian mechanics. The only way we can understand the concept of a photon is through special theory of relativity. We want to see how it is. So, what Einstein accomplished is something extraordinary, which will happen probably once in many, many centuries. He did 3 independent pieces of work, all of them fundamental, all of them very, very original, all of them independent of each other, but still they interact with each other to give us a complete picture of what is happening. So, 1905 was something that was truly revolutionary, and that is something you people should appreciate. So, what has happened? We have reached a crisis in physics. We have reached a crisis of enormous proportion, and all this was started by none other than Hertz. There are very, very interesting stories about Hertz, and apparently Hertz said that he was very unfortunate to have been born in an age where he cannot make fundamental discoveries. Poor man, he thought all that has to be known about laws of nature have been done. Newton gave us gravitation, Einstein gave us, Maxwell gave us electromagnetism, so we understand particles, we understand waves, and then of course you have constitutive equations, permittivity, permeability, everything. Rest of physics was all what? Matter of detail. It is left for ordinary people. So, Mr. Hertz thought, I am an intelligent person, I am talented, but there is nothing much to do for me. He was not the only person who had that idea. When somebody went to Michelson and asked him, should I pursue physics? Michelson told him, no, don't get into physics. Everything is over in physics. We know planetary motion, we know universe, we know everything. Let this all again matter of detail. Somebody will determine something to greater accuracy, greater precision, or whatever. You pursue some other subject. What neither Michelson nor Hertz realized was that they were actually preparing the stage, preparing the ground for what? For a completely new physics which has transformed our lives completely. Einstein came, Planck came, they gave us quantum theory. Einstein gave us special theory of relativity. Einstein gave us general theory of relativity. Today all our GPS, satellite motion is because of general theory of relativity. We have to use them. So this happened not in a smooth manner, but in a very violent way. There was a real deep crisis. So what we shall do is pause for a minute and look at what that crisis is. See, wave nature of electromagnetic radiation has solid experimental support. We cannot doubt that. In fact, it is so solid that even a very, very powerful person, influential person like Newton, who believed in corpuscular theory of light, his hypothesis had to be abandoned. How does he get the solid support from? You have laws of reflection and refraction. You have diffraction. You have interference. These are the experiments which conclusively show that light is a wave phenomenon. And remember, we spent a long time in our second lecture looking at the evidence for all these things. So you have Young's double slit experiment in the visible region. Hertz and J.C. Bose, they repeated the experiment in the microwave region. J.C. Bose and Marconi were able to produce radio waves. Marconi got a Nobel Prize. J.C. Bose did not get. That's a different matter altogether. But we see this way, the region of applicability of the electromagnetic theory, it is working everywhere. So wave nature of electromagnetic radiation has solid support from reflection, refraction, interference and diffraction over a large range of wavelengths, not just in the visible range, but also outside the visible range. So that is very, very firmly established. But on the other hand, photoelectric effect is telling me that I cannot understand this linear dependence on the frequency, the maximum energy depending on the linearly on the frequency from the electromagnetic wave phenomenon. This is the great crisis. Is there a way out? That is what we have to ask, and this is where the 1905 revolution of Albert Einstein is very, very important for us. And what did Einstein do? Einstein said that I will leave all that aside, the problems with waves, etc., aside, and I am going to come up with the particle explanation, a radical particle explanation, and I am going to explain photoelectric effect. At this point, we should remember that Einstein was not aiming at consistency. Consistency is reconciliation of wave nature with the particle nature. Einstein was not doing that, and he was wise enough not to try to do that, because we cannot achieve everything at the same time. The consistency between the wave picture and the so-called particle picture, in fact I should say the so-called wave picture and the so-called particle picture came much, much later in 1930s. So it had to wait for another 25-30 years, and that is something that students of physics study in their very, very advanced courses when they do physics in their quantum mechanics courses. So at this point, please remember that what we are doing is to come up with a viable explanation, but this viable explanation is not completely off the hat. It has a nice rational basis, and you will not be in a position to reconcile between waves and particles. So when you do optics, you will do all interference, double slit experiment, diffraction, etc. When you do modern physics, when you do Bohr model, you will use the photon. But please be patient, you will get to know what it is in your later studies, maybe after another 3 or 4 years. So this is the picture of Einstein when he was 26 years old. So the acknowledgement is Getty images. So all the figures have acknowledgements. Okay. But this requires a prehistory. Einstein did not create the concept of photon. The creator of the concept of photon was none other than Max Planck, and this came in 1900. And I want to spend some time on this, although this is not a part of your syllabus. Now there is something called a black body, concept of a black body in thermodynamics. It is an ideal body, and the property of the black body is that if it is heated to a certain temperature, then it starts emitting radiation. Now normally you take a piece of wood, you take a spoon, you take a piece of paper, and you start burning them or you expose them to heat, their responses are all different. But this black body is an ideal substance in the sense that, ideal object in the sense that at a given temperature the radiation that is emitted is quite independent of what the object is made of. That is the idea of a black body. So it is a kind of perfect body. Now you can think of black body in your imagination. The big question is, do black bodies really exist? It turns out that they do exist, and an excellent example of black body is actually a metal which is white hot. You understand that, no? What does white hot mean? So take a piece of iron, you start heating it, okay? You can go home and do this experiment. You take a spoon and you keep it in the gas flame. It starts becoming what? Redder and redder. It becomes red because it starts emitting radiation in that range. You keep increasing the temperature, it starts emitting radiation in more and more frequencies. And what is white light? White light is a mixture of all these frequencies, therefore it becomes white hot. That is what we mean by white. So a very good example, in fact a very good approximation for a black body is a white hot metal, and that is around something like 3000 to 5000 Kelvin. So you don't see it at 300 Kelvin or 500 Kelvin or 800 Kelvin. So these are the very important experiments which were performed by Lummer and Pringsheim. They built a bolometer which will look at the energy radiated by the black body radiation. I do remember performing that experiment as an undergraduate student. So they built a bolometer and they measured that. And now you ask, what is the energy intensity as a function of the frequency emitted? Because different frequencies are emitted at a given temperature. So for every temperature I will ask, I will plot what is the intensity of the radiation for every frequency. There are other good examples of a black body. An even better example and a better approximation for black body is actually the sun. The surface temperature of the sun is about 5000 Kelvin. So we get about 4 kilowatt of power, is that right, from the sun? The mean power is that. So imagine repeating Newton's experiment of splitting that white light into all the 7 colors and measure the intensity as a function of each of the wavelength or the frequency. That is an excellent approximation for a black body. It will agree very well with what you find with your metal. Sun is not a metal, no? The surface is made of gases. It will agree extraordinarily well. And here in this slide you have a picture of the dependence of spectral radiance or the intensity along the y-axis with respect to the wavelength. So we want to spend some time on that. Okay. I have magnified that so that you people get a feeling. Now you see that if I make use of the classical theory, this curve, the black curve, is the classical theory, and it is telling me, so let us come back to that. You see, the x-axis is increasing wavelength, that is decreasing frequency, and y-axis is intensity. Look at the rightmost curve. This is all at 5000 Kelvin. The rightmost curve agrees with experimental numbers. This is a theoretical curve. The blue, the green, the red, they are all what? They are experimental curves. The red curve is at 3000 Kelvin, the green curve is at 4000 Kelvin, and the blue curve is 5000 Kelvin. Now this black curve is plotted at 5000 Kelvin. So what is happening? If you go to very, very large wavelength, or it is in micrometer, so you are speaking of something like 3 micrometers, or correspondingly very, very small frequency, this curve agrees with the experimental number, which is the blue curve. But as you keep on decreasing the wavelength, that is, as you keep on increasing the frequency, the classical theory keeps on going higher and higher, whereas the experimental number, what is happening to the experimental number? It comes here and it reaches a peak and starts going down. Classical theory tells you that the intensity should go to infinity, it should diverge as the frequency becomes very, very large, whereas experiments tell us no, there is always a frequency at which the intensity is maximum. That is, there is a minimum wavelength at which the intensity is maximum, and after that, if I further decrease the what? If I further decrease the wavelength or increase the frequency, the intensity will go down. So you see that there is a great discrepancy between what classical theory predicts and what experiments are finding. Now, this is not just a matter of discrepancy. This is again a discrepancy of orders of magnitude. In fact, I cannot give even an order of magnitude, because if I want the total intensity, I have to integrate over all frequencies. Now, at any given temperature, my black body has some energy and it is in equilibrium with radiation. So, that radiation should also have a finite energy. But if I integrate the classical curve, because it is going up to infinity, if I integrate the classical curve, I will get a divergent energy. That means at every temperature except T equal to 0, absolute 0, which nobody can achieve, my radiation will be carrying infinite energy, which is nonsense, because we cannot deal with infinite energy, and this is called ultraviolet catastrophe. The divergence is taking place at very, very small frequencies. Smaller the frequency, greater you move to, at very, very large frequencies. Larger the frequency, smaller the wavelength, you are moving towards the violet region. Violet, ultraviolet, X-rays, gamma rays, so on and so forth. Since the divergence is occurring in that region, we call it the ultraviolet catastrophe, and this had to be resolved. So, this is what we call as a pre-crisis as far as photoelectric effect is concerned. Photoelectric effect is not the first example where we ran into trouble. Actually, in 1890s already this problem was there, and Max Planck, whose picture you see here, was one of the great experts on thermodynamics. He said, I am going to understand this, and how do I understand this? I will see what is a model that will correctly fit the experimental numbers, because classical theory will not work. I will have to make a model. That is what Planck said. So, here is a little bit of more explanation for that. Let me go back to this slide and explain that to you, what Planck did, because it is not beyond your reach. Planck hypothesis. So, you have a curve like this. So, this is my increase in wavelength, or this is my increasing energy, because as I move in this direction, my wavelength decreases, my frequency increases. So, increasing frequency. I should not use the word energy, frequency. That is what I have. Now, suppose the same curve was found not for black body but for particles. Suppose the same curve was found for particles. You see there is a peak here, E max, and at both the ends it is going to 0. At both the ends it is going to 0, your spectrum. And this is not surprising from the viewpoint of a particles at all, because equipartition energy tells me the mean energy is 3/2 kT, but at any given temperature, if you go to very, very small energies, the probability is 0. If you go to very, very high energies, the probability is also 0. Why is that so? If you are boiling water, the probability of a water molecule at rest is 0. So, the probability goes to 0. And the probability that at that temperature, one water molecule has an energy such that it will escape from the surface of the earth is also 0. It cannot. So, the distribution is such that it peaks at some energy. That is what we mean by 3/2 kT. It might be something more complicated than that. So, the energy, the distribution of energy, that is what we are going to look at, should fall off to 0 both for very small energy and very large energy. And the mean is at about 3/2 kT. Now, if you look at this experimental result, this is agreeing very well in the classical limit. So, what will Planck do? Planck will say, I will associate, that is very, very important thing for us, I will associate the large wavelength limit with small energy limit, and the small wavelength limit with the large energy limit. That is what I am going to associate. In fact, if you inverted this curve at very high temperature, it will look very much like the Maxwell-Boltzmann distribution as a function of energy. Okay, all that you have to do is to interchange. Lambda will not increase in this direction, but lambda will increase in the other direction. There are small corrections. That is what is going to happen. So what you will like to imagine, and that is what Planck did, is to say that I will look upon my radiation as a gas of photons, gas of particles of light. This is a very crude language, but never mind. Gas of particles of light, and that is what he did. I don't know whether he called it as a photon or not. It was not used. This was called as a quanta. In fact, it was a chemist who introduced the jargon photon much later, after the 1905 paper came, probably around the Compton effect. If you did that, equipartition theorem will tell me that each photon on an average carries an energy 3 by 2 kT. That is what it is. Now, in order to reconcile this experiment, Planck introduced a new constant h, and he said that the energy carried by each quantity is E equal to h nu. So this is the Planck hypothesis. So what are you going to imagine? When I take a black body, something like a metal, heat it to very, very high temperatures, then it starts emitting radiation. There is the Stefan law, which you people have studied. Now, from the classical theory viewpoint, waves of all possible frequencies are emitted. From the point of view of Planck, photons of all possible frequencies are emitted, and the energy of each photon depends on the frequency. E is given by h nu. That is what you are going to have. So this 3 by 2 kT can be related to the nu mean, the mean frequency, and on the either side it falls off. That is what Planck did. This appears like a qualitative explanation, but of course Planck did something much, much better. So he was able to derive this expression for the intensity as a function of frequency and temperature. So you have e to the power of h nu by kT, h is the Planck's constant, and you see that in the limit h going to 0 or t going to infinity, you get back the classical limit. He was able to recover the classical limit, 2 nu squared over c squared over kT, that is one thing. Or if you say that this exponential is much, much larger than 1, if h nu by kT is very, very large, it will look like the Maxwell-Boltzmann distribution. That is what we have. Planck very reluctantly gave this formulation. Does it mean that Planck believed that light is made of photons or particle-like properties? The answer is no, he did not believe. He said that this is an effective way of understanding the interaction between the black body and radiation. There is no doubt that radiation is what? Please tell me. There is no doubt that radiation is waves. Let us not question that. But when the radiation starts interacting with the black body, so imagine black body, a cavity, what is happening? It emits radiation, it absorbs radiation. That is how it is there will be an equilibrium. During this interaction process, it is as if you pretend that it has particle-like property. Like for example, you know, I am uttering these sounds and imagine there are a lot of pulses which are coming. If you don't resolve the width of the pulse and if you don't look at it very carefully, it is as if, you know, the bullets are coming and hitting your ears if I am shouting very, very loudly. So you pretend as if it is particles, but deep down what is it? It is nothing but what? It is nothing but a wave. So this was some kind of an effective description which should be understandable, which we should be able to explain by working out the details of interaction between the black body and radiation. But fundamentally speaking, what did Planck believe in? Planck believed that radiation is only a wave-like phenomenon. Planck did not believe in the concept of a photon or a quantum. That is something that we have to remember. So this is where the Einstein revolution comes, because not only was he trying to give an explanation in terms of the concept of a photon, he was actually propagating, advocating that photon is real. That is the most important thing. He said we should take the concept of a photon very, very seriously. So the difference between Planck and Einstein is that they make use of the same hypothesis. Planck thinks it is some kind of a make-do phenomenon. I am making a tentative explanation, we will not take it seriously. But Einstein is saying, no, we are going to take it seriously. We are going to assume that radiation is like a gas of photons, each photon carrying an energy h nu depending on what it is, and I am going to explain photoelectric effect. And that is the reason why after about 20 years, around 1921 or 23, 15, 16 years, Einstein got a Nobel Prize for this photoelectric effect. So what is the reconciliation? So the reconciliation is in writing these two expressions. The classical expression for my energy density is given by epsilon naught by 2 E naught squared. But for photoelectric effect, we are going to write it to be the number density of the photons multiplied by h nu. So what are we saying? Classically speaking, there is a plane wave. Let me explain that. So we are looking at classical quantum. Classically, there is a plane wave. It is carrying energy, and u is given by epsilon naught by 2 E naught squared, the mean energy. This is classical. Quantum mechanically, you have stream of particles. So this is frequency nu. Associated with this frequency nu, you have a stream of particles coming with energy h nu, and u is the number density of the photons into h nu. Number density of the photons multiplied by the energy of each photon will give me the energy density. So what will I do? There is a classical expression, there is a quantum mechanical expression. Classical is coming from a wave, this is coming from particle. Wave has nothing to do with particle, particle has nothing to do with wave. But we are courageous people, I mean Einstein was courageous. We are going to equate the two of them. That is how you solve all your problems in your 12th standard for your JEE or CBSE or anything. So given u and given frequency, you can find n gamma, so on and so forth. This is the radical proposition by Einstein, and we are going to see that with this simple identification, however illogical it may be, we will be in a position to understand the photoelectric effect. We need a few hypotheses. They are all reasonable, and what we shall do is to start listing them. So that is what I have collected in this particular slide. The Planck hypothesis is a reluctant explanation taken to be of limited validity and limited applicability, but not the Einstein hypothesis. So what I will do today is to simply state the hypothesis. I will not go beyond that. And in the next lecture, I will elaborate upon that. I will show how the Einstein explanation correctly and completely explains the photoelectric effect. And I will also give you one application, that is the Stokes law, that will conclude our study of the photoelectric effect. And after that, we go on to the Bohr model, where again the concept of a photon will become very, very important. So what are the assumptions that we are going to make? And let us stop here. So I have written that down here so that we can read them at leisure. The incident radiation of frequency nu can be looked upon as a stream of photon gas with each photon carrying an energy h nu. That is the Planck hypothesis. Now comes the 2, 3, 4 refer to what Einstein invoked, what Einstein postulated. We say that electrons in the metal escape to free space by transfer of energy from an individual photon. So what are we saying? My electron is in this metal. This photon comes, I am not writing the wave picture. My electron absorbs the energy and it comes out. So it is a collision between an individual photon and an individual electron collision between individual photon and electron. The second assumption that we have to make, and that is a very, very reasonable assumption, is that energy is strictly conserved in this process. No problem. But the third assumption is very, very crucial, which is not often mentioned in books or in lectures on photoelectric effect. The maximum kinetic energy of the electron corresponds to complete absorption of the photon. So you can imagine a situation. A photon comes, my electron is here. Electron gets a part of the energy and photon continues. So the energy of the photon will be depleted. That is perfectly possible. So this is what we call as a collision. So my electron is coming here, my photon is coming here, electron gets the energy, some energy from the photon, and the photon propagates. But the complete absorption means this does not exist. All the energy is gobbled up by the electron. That is a very, very important assumption for us. So if you make these three assumptions, then the explanation for the photoelectric effect becomes quite easy, and we will take that up in the next lecture. So let us stop for today. Have a good day.